And hello, everybody. Um, First of all, for Covenant Life students, this year, and probably this year only, in order to expedite things, we will be skipping chapter 11. It's an interesting chapter, pretty cool stuff in it, but I would encourage you to read it on your own. There will be no test on chapter 11. Likewise, I always skip chapter 12. Why? Because chapter 12 is boring. Paul Hewitt himself says, if you're going to skip chapter 12. Chapter 12 is about solids. What do solids do? They just sit there and do nothing. So solids are very boring, I think. So Paul Hewitt says skip chapter 12, so we'll skip it as well to save some time. So we're going to dive right into chapter 13. But first, an encouraging word. I got an email this morning. And you might think that I made this up myself, but I did not. This is a real email I got this morning from one of my homeschool students. And I thought it might be an encouragement to you for your future. She says, "Thank you, Mr. Peer. Our family knows that the level of your course far exceeds a typical high school level physics course. Our son Miles, who took your class 4 years ago, is now taking UMD Physics 3 as an aerospace engineering major. As I told you in a previous email, he credits your course for his ability to do well in his college physics courses. So thank you for all you do, as it is a gift to have our children have you as their teacher. God bless, Carolyn." So that was very meaningful to me. I received many similar emails over the past. So just let it be known that even though this is not a math-based physics course, it is a fabulous preparation for the math-based courses you'll take later, probably in college, and a great preparation for things such as aerospace engineering. And I know I have one past student who, last I heard, was a nuclear engineer on a nuclear submarine, and likewise credits Paul Hewitt's conceptual physics for his success in that field, and many other examples. So take heart. Even though this may not be what some of you were hoping for, it's not jam-packed full of mathematics, it's still an incredible preparation for the math-based classes. We move on. Definition of fluid. A fluid is simply that which flows. If it flows, it's fluid. Gases and liquids are both fluids. When we think of the word fluid, we normally think of a liquid, right? Fluid, liquid, yeah. But gases are also fluid because gases, the air that I'm swimming in right now, they flow. So gases and liquids are both fluids. This is going to be more important in chapter 14. For right now, we are concentrating on liquids. By the way, liquids are nearly incompressible. I think I've got the difference here. Yes, in a liquid, the molecules are free to slide around each other. Of course, in a solid, they're locked in place. That's why a solid doesn't flow. But in a liquid, the molecules are free to slide around each other. And because of that, it flows. And also because of that, a liquid will fill up and take the shape of its container, such as this water right here. Yeah, it's real water. This water right here taking the shape of its container because it flows. What's that green arrow say to do? So yes, that also liquids are nearly incompressible because how much space is there between these molecules as they slide around each other? There's practically no space between them. So it's incompressible. You can squeeze water and it will not get smaller. You can squeeze a gas easily and it'll get smaller. It'll lose volume as you squeeze a gas. But, and we'll get into more of that in the next chapter. But liquids, you try to squeeze it, and it's like hard as a rock. You can't compress a liquid. All right, now, let's get into this. Definition of pressure. You're probably familiar with this. Pressure is force divided by area. What does that mean? Well, consider the fable of the ant and the physics text. And for this, I need to change the camera. I do not have a camera operator, so I'm going to have to operate it myself. All right. Consider, pardon the Yes, I have disinfected this recording, so you don't have to worry about getting coronavirus from this recording. Consider an ant walking across the table. When I was a kid, we used to play with ants because we didn't have internet, you know? So if you don't have internet, what else are you going to do? You're going to go in the backyard, you're going to play with ants. And we would take a little handful of dirt, pour it on top of the ant, and watch the ant climb out of the dirt. Kind of fun. Ants are pretty tough. You put an ant on this table and lay this book on that ant carefully and lift the book up, and the ant is most likely going to crawl away because ants are pretty tough. But if I take the same book and put it on the ant like this, he might still survive, but he's going to have a rougher time. But what if I take the same book and put it on the ant like this? Okay, I'm pretty certain that ant's going to be squashed. What's the difference? It's the same book. Well, it's a question of definition of pressure. Pressure is force, the weight of the book, force, divided by area. Laying flat, the area is large, so the pressure is small. Like this, the area is much smaller, so the pressure is greater. Like this, the area is very small, so the pressure is very high. Enough pressure to squash the poor little ant. This might be, I'm going to guess, 2 pounds. 2 pounds per a few square millimeters. Whereas this was 2 pounds per a lot more. Now, let me redirect the camera here. Okay, that's pretty good. We got it. Okay, and go to the next screen. We now have the fable of the elephant and my mother. Yes, a very well-known fable. Suppose we have an elephant, and I did some research, found out that it's reasonable to have an elephant with a weight of 16,000 pounds, which is incomprehensible that you got an elephant that has a weight of 8 tons, but I looked it up, and that's what the internet said. And of course, the internet is always right. Typical African elephant's foot diameter is about 16 inches. 16 inches across, about like this. All right. That means if its foot diameter is 16 inches, multiply by pi r squared, and you get approximately 200 square inches under an elephant's foot. Now we're going to be talking here about a circus elephant. Yeah, I guess circus elephants don't exist anymore because of animal rights and all that. Back in the old days, you would have an elephant that was trained to stand on 1 foot. Yes, they actually did that. It's pretty cool. An elephant with all of its weight on 1 foot. All right, that being the case, if we have an elephant standing on just 1 foot, then what's the pressure under that foot? Pressure is force divided by area. The force is his weight. Weight divided by area. 16,000 pounds divided by 200 square inches under that foot. Divided out, you get 80 pounds per square inch. What's that mean? Underneath the elephant's foot, on every square inch of area under his foot, there is 80 pounds of force. 80 pounds of force on every square inch. That's a bunch of pressure. Now, let's consider my mother. Keeping in mind that an elephant's pressure is 80 pounds per square inch. My mother, when she died, she weighed probably about 100 pounds. She was a little thing. She was very short and very skinny. And we're going to put my mom on high heels and let her lean back on those high heels. Okay, she's going to lean back on the heels. I know it's kind of difficult, especially for a little old lady, but we'll help her. We'll steady her with our, we'll hold her shoulders. But she's going to lean back on her high heels. And I don't know a whole lot about high heel shoes, but I'm going to assume that if this is a square inch, I'm going to assume one high heel is maybe about 1/4 of a square inch. So if we have 2 high heel shoes, we're talking about 2/4 or 1/2 of a square inch. I'm just estimating. I've never actually measured this. So we'll assume that my mom is standing on about 1/2 inch square inch. She's tipping back on both shoes. Both shoes, that'll spread the pressure out some more by doing both of them. Okay, so what's the pressure under my mom's high heel shoes? Force divided by area. 100 divided by 1/2. Ah, but wait a moment. How do we divide by a fraction? Do we not then multiply by its reciprocal? Yes. Wait, no, that can't be. Ah, but it is. 100 times 2. Yes, the pressure under my mother's high heel shoes is 200 pounds per square inch. What does that tell you then? If the terrorist says to you, "We are going to torture you to make you talk," if you do not, is this what terrorists sound like? I don't know. If you do not talk, we give you two choices. You can either have the elephant stand on your foot, or you can have my mother stand on your foot with high heel spikes. If they give you that choice, take the elephant. Because you know that the pressure under the elephant's foot is less than half the pressure under those high heel spikes. Those high heel spikes might just poke right through your foot and go all the way to the ground. Whereas the elephant's going to be kind of like, "Oh, hey, get off my foot, that hurts a little bit, you know." Ah! But with my mom's high heel spike, it's more like, "Ah!" Excuse me. My seasonal allergies, not corona, my seasonal allergies didn't like that scream. Okay, so that's to emphasize the concept of pressure. Force divided by area. It's not just force, it's not just weight, but it's how that weight is spread out over an area. In fact, I should have thought to bring this down. Maybe next time I'll remember to bring down my little miniature bed of nails. But you can put a balloon on a bed of nails and pile books on top and it won't break, because the force is being spread out over a whole bunch of little nails. So the pressure over each nail is actually very small. More could be said about that, but I will spare you the details. Oh, by the way, there is a picture. I do not know the page number. Did I by any chance write it down here? I should have. There's a picture someplace in the book. I do not remember where it is. You can maybe flip through and find it for yourselves. But there is a picture of Paul Hewitt, actually a friend of Paul Hewitt, laying on a stage on top of a bed of nails, with another bed of nails on top of him, with all the spikes going this way and this way. He's laying down between two beds of nails, with a cinder block on top of the top bed of nails. And Paul Hewitt himself has a sledgehammer, and you see a picture of him smashing the cinder block with the sledgehammer while his friend is between the beds of nails, and no harm is done. Partly, there are multiple things going on there, but it's partly because the pressure on a bed of nails is low enough under each nail that no one nail has the ability to even poke through your skin. Because there's so many of them, the pressure is spread out. So, pressure is not just force, and it's not just area, but it's force divided by area. We move on. By the way, where am I? I am on page 247 right now. Density. Definition of density: mass divided by volume. For instance, water. 1 liter of water, which is about what this is 1 quart, but 1 quart is very close to being 1 liter. 1 quart of water, 1 liter of water, has a mass of 1 kilogram. So the mass of this 1 kilogram and the mass of the water are the same. I could weigh these and find out they are the same. Actually, I'd have to subtract out the weight of the glass itself. But the water weight here is the same as the weight of the 1 kilogram mass. In other words, this is far more dense than water. But water is far more dense than, say, air, for instance. So that's the meaning of density. Density of water is 1 kilogram per liter. Now, that being the case, what about something called weight density? We're going to be dealing with weight density because for us it's going to be more convenient. Weight density is weight divided by volume. Not mass divided by volume, but weight divided by volume. Makes sense? So 1 liter of water, which has a mass of 1 kilogram, if it has a mass of 1 kilogram, you'll remember to find its weight, you multiply mass times gravitational acceleration. So multiply by 9.8, or about 10. So the weight of 1 liter of water must be 1 times 10, or about 10 newtons. So this has a weight of 10 newtons. The water also has a weight of 10 newtons. So water's weight density is 10 newtons per liter. Yes, water's weight density is about, it's actually 9.8, we'll call it 10. Water's weight density is about 10 newtons per liter. That being the case, let's go back to this now. Oh, what time is it? I want to cut this off at the 30-minute mark, since my camera cuts me off every 30 minutes. Pressure is equal to force divided by area. We've already established that. Therefore, in the context of water, we're talking about liquids here. We're talking about the pressure in water. If you're underwater, you feel that pressure. I personally don't like going down underwater. I'm not a water person. I don't like the feeling of the water pressure on my ears. I hate that. Oh, you just have to go. Oh, no, I don't want to do that. No, I hate that feeling. I prefer to stay on the top of the water. But anyway, we're talking about pressure in a liquid, pressure in water. As you go deeper, pressure gets greater because you have more water over your head. The deeper you go, the more water there is. And the more water there is, the heavier it is. And the heavier it is, the more pressure you're going to experience. So, back to this. If pressure is force divided by area, and force in this context is going to be the weight of the water. So pressure in the liquid is going to be its weight divided by the area. But wait a moment. Weight equals, anything's weight is going to be equal to its weight density times volume. I'm not going to take time to elaborate on that. If you don't see why weight will be equal to weight density times volume, find it on Khan Academy and look up density or something. But just trust me on that. Assuming that is correct, and it is, we have the following. Pressure is force divided by area. Well, that means that pressure is weight divided by area because the force is the weight. But if weight is weight density times volume, then I simply change the word weight into weight density times volume. But wait just a moment, we're not done yet. Because, consider this. Oh, we're leading up to a formula you must have memorized. But, what's volume? The volume of an object is the area underneath it here times, fill it up, area times depth. Area times depth. That's a little bit of geometry. You can look up that under geometry on Khan Academy if you like to. But the volume of this container is the base area, fill it up, times the depth. Volume meaning how many little cubes of stuff are in here. Alright, so if that's the case, if volume equals area times depth, let's go back to this. Let's change the word volume into area times depth. So we've got this really nasty looking formula, a lot of words here. If pressure is now weight density times area times depth, all divided by area. Do you see something clever in that? I do. You're about to. Watch this. As I change colors, what color would be? Let's use red. Watch this. I've got this nice neat fraction here. I can cancel out area. Area divided by area cancels. What am I left with? I'm left with pressure equals weight density times depth. Notice I'm not canceling out this whole thing. I'm only canceling out the area. So pressure equals weight density times depth. There is the formula. for pressure in a liquid, pressure in a liquid is weight density times depth. A fairly simple formula. There's something to notice about this that's fascinating. Where in this formula do you see anything about how wide the body of water is? It's not there. And because liquids are nearly incompressible, it doesn't matter how deep you go, the weight density is going to remain constant in a particular liquid. Now, different liquids have different weight densities. For instance, mercury. Mercury has 13 times more weight density than water. That's kind of hard to comprehend. But weight density in one given liquid is not going to change. So that remains constant. The only thing that's going to change is depth. So the only real variable in calculating pressure in a liquid is how deep are you? It doesn't matter how wide the body of water is. It doesn't matter the shape of the body of water. All that matters is how deep are you in that water. So a thought went through my mind. It was hitting me as being an important thought. Okay, that being the case, oh, by the way, in much of my discussions here, I'm going to ignore one actually very important detail, but to simplify things, I'll ignore it most of the time, and that is this. When you're talking about the pressure in a liquid, suppose this is a container of liquid here. If I'm located there, I have a particular pressure. The weight density of the particular liquid, perhaps 10 newtons per liter if it's water, 10 newtons per liter if it's water. I'll spell that out. Multiplied by the depth, how deep am I in this liquid? And using the metric units, that would have to be measured in meters. How deep am I? If I go down twice as far, my pressure down there will simply double, right? Twice the depth, twice the pressure. But I need to hasten to add that that does not take into account the weight of the air also pressing down on the water. We're going to be ignoring that for simplicity's sake, but it's important for you to recognize that the total pressure in this liquid is not just the liquid pressure, it's the liquid pressure plus the air pressure. And air pressure is significant. In fact, as we'll talk about more in the next chapter, the pressure on the surface of this water from the air alone is 15 pounds on every square inch. No, yes, 15 pounds on every square inch of the surface of this water. So we're ignoring that though, just to keep things simple, okay? We'll pretend that we're in a vacuum and it's just the water alone. So you go down twice as far, you're doubling the depth, you're going to double the pressure. Now here's the cool thing. Suppose I am at the beach and I go down maybe 1 meter in the water. This is me, 1 meter down. Consider the size of the Atlantic Ocean. Consider how much water we're talking about. Now, on the other hand, I have a very deep bathtub. I don't think bathtubs, 1 meter deep bathtubs exist. But suppose it did. If I've got a little bathtub here full of water, and I go down 1 meter in this water, this is 1 meter down in the water. How do the pressures compare? 1 meter down in the Atlantic Ocean or 1 meter down in a bathtub full of water? The pressures are the same. Because the only variable here is depth. There's nothing here about how wide the water is. There's nothing here about the shape of the container. In fact, consider this bizarre concept. If I have a container shaped like this, full of water, and I'm located here. Or suppose my container is shaped like this, and I'm located here. If the depth from the surface here is the same as the depth from the surface here, the pressures will be the same. In fact, if I have a container shaped like this, and I'm located here, if this depth is the same as this depth, the pressures are going to be the same. The pressures will be the same. Because the shape of the container and how much water is involved has nothing to do with it. Well, how much water is involved? Yes, if I have a container that's shaped maybe like this, that contains very little water, and I put myself, let's make that water not so, I want it to be this deep. This deep. Okay, the water's right there. And if I'm located here, very little water in this container, yet if this depth, I'm destroying here, if this depth equals this depth, the pressure here is the same as the pressure here, is the same as the pressure in the Atlantic Ocean if the depth is the same. The shape of the container, the amount of water has nothing to do with it. The only variable is depth. Very important and a pretty cool concept. And checking the clock, it's about time to stop, and I think that works out pretty well. That may have been my last, yeah, that was my last. Hey, I'm done for today. We could continue on, but we'll stop there. That pretty much takes us up through page 248. Oh, I've got a couple minutes left. You want me to throw this in? My body is a liquid container. My blood vessels contain liquid, from the top of my head to the bottoms of my feet. In fact, if I put my hand up here, right now, the top of my hand is very, very high in this container. The depth is very small, so the pressure here is very low. And if you were to see my hand up close, you would see that my veins are all pretty flat. However, if I put my hand down low, where my hand is now deep in this container of blood, and if I give my hand a chance to equalize there, or to settle down some, whatever you want to call it, because my hand is now down deep, you can't see it, but you will in a moment, because my hand is now down deep in this container of blood, the pressure is greater. Because the pressure is greater, look what my veins have done. Do you see that before they go back down again? I don't know how much you got to see of that because I wasn't looking. But my veins all popped out and looked really nasty. I don't like doing it because it's kind of gross looking. But that's why they say if you've hurt maybe you've hit your thumb with a hammer, bam, oh, and it's throbbing with each heartbeat. You feel it, oh, that pain. Put your thumb up high. Why? Because up there the blood pressure is less and the pain is going to be less. You put your thumb way down there, it's going to hurt a lot more. Or with a headache. If you stand on your head while you've got a headache, it's going to be worse because you've got more blood pressure in there then. So you want to be more vertical, or at least lying down, but you don't want to put your head down low. Why do you put your head between your knees when you feel like you're going to faint? Because what causes fainting is when you get a lack of blood flow in your brain and you start to put your head between your knees. Why? You're lowering your head in that container of blood, making the depth from the top of the container to your head greater, thus increasing the pressure. Because the shape of the container has nothing to do with it. It's all about how deep you are in that container. The only variable is, okay, I've lost it here. Well, yeah, what did I do to my formula? The only variable is depth. This is gone. So there's our formula. If you want to see it again, pressure equals weight density times depth. Now, of course, if we have a different weight density, such as mercury, then the pressure is going to be 13 times as much. Yeah, you go down 1 meter in mercury and you're dead. Well, mercury is probably going to kill you anyway. But if you could go down 1 meter in mercury, the pressure would just squash you. We can't handle that kind of pressure. 13 times the pressure of water. Goodness, that's like going down 13 meters in the water. Okay, so that pretty much takes us all the way to page 249. We'll pick up on page 249 in the next video. I'm planning on breaking this video into, 3, 4, or maybe even 5 parts. This was part 1. So, have a good day, and we're done for now. Thank you. Bye-bye.